A session has already started. All right. As usual, I'm setting Adelia as co-host, Alif as co-host. All right. Please help me to admit those people who's not using MOE account. Okay. All right. So right now we're gonna enter refraction of light. Actually, I have my previous notes from refraction of light that I used last year for the Form 5s online. But because of due to time constraints, so I have to use the shorter express version. Okay, so hopefully by me explaining and breaking down the words from the textbook for you guys will be able to understand it properly. Um, Also, reflection, this light chapter is an extension from the wave chapter. That's the reason why you learn regarding the wave first, then only now we're talking about light. It's an extension. Why? Because in wave, we study about three different type of wave. We have light wave, water wave, and also sound wave. And if you would notice, majority of the discussion in the wave chapter was mainly on water wave and sound wave. All right, so the main reason is because the last chapter in Form 4 is regarding light as a wave. Okay, so over here, the first part that we're going to be learning is actually refraction of light. So an example, if you were to put a pencil inside a cup of water, all right, a transparent water, glass, uh, glass, okay, wait, my head a bit. Okay, if you put a pencil or a pen inside a glass of water, the pencil will appear to be bent. Or if you put a pencil behind a glass block, you can see that the image is actually slightly moved away, right? This phenomena is actually called refraction of light. So, okay, now let's go next. So, the phenomena known as refraction of light has a few things that we have to understand. In the previous topic of wave, refraction of wave, sorry, in the chapter of refraction of wave, we talked that refraction of wave occur due to the change of speed. All right, speed of the wave changes, so it actually changed direction. So when we talk about light wave also here, it is the extension from wave. So refraction of wave occur due to the change of the velocity of light. All right, over there, they did also mention the word velocity, also can be speed. So over here, the difference between velocity and speed is that speed is a scalar quantity, where velocity is a vector quantity. Meaning means that not only the magnitude changes, but the direction change as well. All right, so when traveling from mediums of different optical densities. Now, optical densities we will discuss in the next slide. All right. Optical density is slightly different from a physical density that you learned previously. All right. So a picture, an example picture would be this. Okay. Or let's see if my simulation is up and running. All right, a simple example would be this simulation. If this part, it is actually, the medium is actually air, the index of refraction is actually 1, and the bottom part is actually water, index of refraction 1.33. You would recall learning this a little bit from, I think, from 1 or from 2. Okay, but we are refreshing everything back again. So when I actually switched on the laser pointer, all right, it will incident from at this particular surface boundary, and it will be slightly, the rays will actually change. Okay, the rays will actually change if I were to put a protector over here. All right, so let's just say if I put the angle at 30 degrees. Okay, so as you can see over here, it is slightly different. All right, it is not at 30 degrees, but slightly less, around 21 to 22 degrees over here. All right, so the angle did change. The light ray, instead of going in a straight line, but when it went to different boundaries, it actually changed its direction, the angle as well. All right, so if in terms of velocity, let's just say in terms of velocity, we have air on top, and this is also water. So if I want to see um the speed All right, this simulation uses some toy car to actually shows that it's actually moving much more slower. All right, you can actually see that comparing to this part, the toy car right now is actually moving much more slower and much more closer to each other compared to the previous one. All right, they are trying to represent the wavelength. So when it moved from a less dense region to a denser region, here it actually went closer and it moved much more slower. Okay, so that is an example. We will go back into that in a short while. Now, refraction actually obeys the law of refraction, right? Even though the law of refraction was not introduced in the wave chapter, but it is introduced in the light chapter. And I remember, should be at a lower form, you have learned this as well. So, laws of refraction have two statements, right? When light travels from one medium to another medium, which has different optical density. Again, we will explain what is optical density in a short while. The first statement is that the incident ray. What is the incident ray? The incident ray is actually this line, the arrow that pointing, the starting arrow. Now, this starting arrow means that the object is located here. Why? Because when we learn about light ray, the characteristic of light ray is that it moves in a straight line, right? Light ray actually move in a straight line. Then light ray, right? Our rays will come from the source of the light, and then after that, it will shine onto the object, and then from the object, it will move towards the image. All right. So that is one thing regarding light ray, okay, or light wave. So over here, okay, the incident ray, this is the ray. Ray means a straight line, okay? Ray means the light wave is actually moving in a straight line. Incident ray means the first one, the arrow will point towards the boundary. And then after that, the refracted ray is after crossing the boundary, it's called a refracted ray, all right? Refract, pembiasan. And then the normal line is actually the dotted line that is 90 degrees to the boundary of the surface. These three rays at the point of incident all lies on the same plane, which means all line at the same axis, as what we can see right now is on the x-axis. Okay, so that's the first statement of law of refraction. The second statement of law of refraction is that the ratio, all right? Ratio means sine of the incidence angle or sine I. Ratio means over, right, to the sine of the angle of refraction, sine R, is a constant value. So that constant value, I let it be n. All right. So what is incidence angle? Incidence angle is from the normal line. We measure from the normal line to the incident ray. Refracted angle is we measure from the normal line to the refracted ray. All right. So this is refracted angle R, incidence angle I. Okay, so please remember the angles are measured from the normal line to the ray itself, not from the boundary. All right, so please clear with that. Students always confused. They always thought that this is the incident angle. This is not, because this is actually the boundary. Incidence angle is measured from the normal itself. Okay, right. Now, next, what is optical density? Okay, optical density that was given in the textbook, they said that optical density is not the same as the density that is defined by mass per unit volume. Now, mass per unit volume means the symbol of density equals to mass over volume. All right, this is physical density. Okay, this symbol density, which formula is mass over volume, this is known as a physical density. So when we talk about light wave moving in different optical density, we're not talking about the mass per unit volume, but it is actually a property of the property of a medium. Okay, so where is my pointer again? Okay. If you suddenly see scribbles on the screen, it's because I'm trying to find my pointer. All right, so for example, the density of oil is lower than the density of the water. That's why the oil floats on the surface of water. But when light is shined onto oil and water, the optical density of oil is actually higher than the optical density of water. So it's two different characteristics, two different physical quantity. All right. So optical density, like any wave, the speed of light wave is dependent upon the property of the medium. So in the case of electromagnetic wave, now remember in the previous class I did mention electromagnetic wave, we have a spectrums of gamma ray, then we have UV ray, if I'm not wrong, we have gamma ray, UV ray, visible light, then we have infrared, microwaves, and also radio waves. Okay, I think I missed out one. Okay, so this is actually a spectrum of electromagnetic wave. So electromagnetic wave, thank you, Adelia, X-ray. Okay, X-ray is here. Okay, so the speed of wave depends on the optical density. All right, because in the previous chapter, when we talk about refraction of light wave, the speed of light wave depends on the optical density. So in this case, all right, the optical density of a medium is not the same as the physical density. More optically dense, which a material is, the slower the wave will move through the material. Meaning means the optical density increases, the wave speed decreases. Okay, I repeat, if the optical density increases, the speed of the wave decreases, right? It will move much more slower. Okay, so now let's look back at the simulation that I had just now. All right, for this simulation that I have, okay, the top is air, the bottom is water. Based on the movement of this toy car, all right, which one has a higher optical density, air or water? Answer in the chat box. Air or water have higher optical density? All right, majority is saying that water has higher optical density. Good. Okay, so now let's proceed next. Okay, so we need to understand refraction of light. So refraction of light is a phenomena where the direction of light changes as it crosses the boundary between two materials of different optical density. All right, the speed changes. Remember previously when we talk about the speed changes, the wave speed change because of the wavelength change. So the wavelength actually changes because of the medium change. So we are talking about light wave. So when we talk about light wave, the wave speed changes because the medium changes optical density. So later on, whenever we say less dense medium to a denser medium, we're talking about the optical density here. We're not talking about the physical density of mass over volume. Okay, so like for example, the next thing is actually the change in the velocity of light as it passes from one medium to another medium. So here I want to clarify some things regarding refraction of light. So what does the word means and what does it corresponds? Now, even though I mentioned it just now, angle of incident, all right, the angle of incident is located here. Angle of incident is the angle between the incident ray and the normal line. So the arrow that points towards the boundary, the blue color arrow A, this is the incident angle. Sorry, this is the incident ray. So the angle between the normal line and the ray is actually known as the incident angle. Then the red color arrow B, that is the one that has that ray, that line has already crossed the boundary and it actually moved away from the normal line. So this is known as the refracted ray. The the refracted angle is actually from the normal line towards the refracted ray. So that is actually the symbol R. So please do note the normal line is 90 degrees to the surface. Okay? If let's just say incident angle less than the refracted ray, let me erase everything off. When the incident angle is less than the refracted ray, which means that, more than the refracted ray, it's actually here. All right. When the incidence is actually more than the refracted ray, the ray bends towards the normal. All right. The ray actually bends towards the normal. That's why the refracted angle is much more less. And when it bends towards the angle, the speed of light actually decreases. Okay. When it bends towards the normal, the speed of light actually decreases. Then after that, okay, if the refracted angle is less than the incident angle, situation like this, moving from a denser medium towards a less dense medium, the no wonder I keep explaining one thing, but then this thing sudah salah. The symbol is supposed to be R greater than I. When the refracted angle is actually more than the incident angle, which is actually denser medium towards the less dense medium, the ray actually bends away from the normal line. It moves further away. Now, how do we actually see that it moves further away? In exam, right? In exam, what you do is, I'm going to show you at the normal slide here. In exam, how do we know that whether is it moving away or closer towards the normal line? So all you have to do is take your ruler, place your ruler at the incident angle, right? Because we already have a normal line over there. So if let's just say your incident ray is like this, and then your refracted ray is going further away from the normal line, all right? So we know that this is moving away from the normal line. So if like this is our incident ray, our normal line is down here, and you notice that the refracted angle is actually closer towards the normal line. Okay, so that is actually moving from less dense to denser medium. Okay, so this is actually how I usually identify whether is it moving away from the normal line or is it moving closer to the normal line. Okay, now let's get back to our slide. Okay, so when the light ray is incident normally on the boundary between the two medium, the light ray does not bend. Okay, why? Because it incident normally 90 degrees to the surface. So I'm going to prove this out to you. Okay, so I'm going to just use this because it's easier for me to move it. I'm just going to put like this. And you do notice that the light ray is incident from the laser source towards the boundary of the surface and it goes down all the way. All right. So then you would be thinking that maybe because the material is different. So I can change the material even if it's moving from glass. All right. It's moving from glass to water. It's still moving in a straight line. If you incident normally, it doesn't matter which side is it going, it still will become 90 degrees. Incident angle 90 degrees, refracted angle 90 degrees as well. Okay. If it's normally, this is what will happen. All right. If it's incident normally onto the boundary, it will be a straight line. The light ray does not bend at all. So this is one tips for you guys, one indication for you guys that you have to understand. Now, because students normally go and memorize less dense to denser, denser to less dense, but they've forgotten what happens when the light ray incident normally onto the surface. Okay, now we are moving from less dense optical density to a denser optical density medium. All right, we are moving from a less dense to denser. Less dense to denser normally is air. All right, air to any other materials or vacuum to any other materials. So the incident ray comes, incident angle, and it will be refracted closer towards the normal. Now, when this happened, okay, first thing that we need to know is that it's moving from less to denser optical density. Okay, so when it's moving from less dense to a denser optical density, the wave speed decreases. Because what we have already mentioned previously, the wave speed will decreases. When the wave speed decreases, what other characteristic that you have to remember? You have to remember that the refracted ray moves, if you would notice, closer to the normal line. Right? These are the three things that you have to remember. And please don't forget the arrow. All right, when you draw a ray diagram, this is also considered as a ray diagram for refraction. You have to have the arrow. The arrow shows that where is the ray moving, where is light moving from. If you don't put an arrow over there, unfortunately to say, you won't get any marks if this question comes out in your any exam papers. All right, so please do take note on this. Okay, so this is actually moving from a less dense to a denser optical density medium. Okay, next we are going to denser. All right, the ray right now, light is actually moving from denser to less dense optical density. Again, this is not the physical density of mass over volume. Please do take note. So when you're moving from denser to less dense optical density, number one, okay, what can we see? It's moving from less dense to denser. The speed, all right, the speed of the velocity, all right, of the light wave is actually increases. I'll tell you an analogy later for you guys to understand. The speed will increase, and then another thing is that the refracted ray will move away from the normal. All right, the refracted ray will move away from the normal line. So you would see that this one goes further away. If the question asks you to sketch, you can just sketch roughly moving away. You don't have to measure the incident and the refracted angle. If the question asks you to draw, then only you need to identify the angle. If they have calculated, ask you to calculate it at above. Normally, we don't measure exactly how much the angle is. We just move the ruler away from the normal line to indicate that it's moving from denser to less dense region. Okay, so that is for the concept for refraction of light between densities. Now, how do I actually identify moving from, let's just say, less dense optical density towards a denser optical density? Now, when moving from a less dense optical density to a denser optical density, we said that it actually moves slower. All right, it becomes slower, the speed becomes slower. And then after that, we say that it moved the refracted ray is actually moving away, not away, sorry. It should be closer towards the line. All right, closer towards the normal. So let's just say when we're talking about the F1 car, okay, there's a reason why I use F1 car, because light wave move very fast. F1 car also move very fast, ma. Okay, so if the F1 car is actually moving at this normal path at the road here, this normal path, all right, they has lower friction compared to the outside terrain, the side terrain. This one has a lot of dust, a lot of loose grains and sands and everything, so they have higher friction. So this is analogy to the less dense and the denser. So when the F1 car is actually moving at this path and they sidetrack towards the roadside, what will happen is that they will definitely slow down because the friction increased already, ma. All right. If it moves just on the highway, it can move very, very fast because there's less friction. But then when it moves towards the roadside area, this path, it will actually have high friction. So the speed of the F1 car will definitely slow down already. And when it slow down, normally the F1 car, they cannot move further away, all right? Assuming this is the normal line up. It can only move very close towards this line, the boundary line, okay? Remember here, I'm using boundary, not normal line. It will actually move towards here, all right, further away. So this is actually when it's moving from less dense to denser. But what happens if the opposite direction? All right, opposite direction means the side of the road has high friction. So the F1 car initially moving here, all right, at a slower speed because there's a lot of loose grains and loose sands over there. So it's actually high friction area. And then when it actually moved towards back to the highway, all right, highway less friction. Less friction means it can actually speed up. Higher speed. When it's higher speed, and one more thing, because it's higher speed already, it's easy for them to actually move away, further away, from the boundary there. All right. So this situation is whereby it's moving from a denser to a less optical density region. All right. When it's moving from a denser to less optical density region, the wave speed increases. And when the wave speed increases, the refracted angle, the refracted ray, actually move closer to the normal line. All right, so I hope that this analogy will give you guys a easier method to memorize moving from less dense to denser, or denser, the light ray moving from denser region to less optical density region. Okay, so at the very least, at the speed, the speed part, it would be easier for you to understand. All right, because it's slightly different compared to the water wave that we learned previously. All right, because light wave, when it's moving from a less dense to a denser region, the speed actually slows down. Okay, so this one, I hope you guys are okay. Are you guys okay with this analogy?
Sure.
Mm.
When it goes from denser to less dense,
Mm-hmm.
the refracted ray is further from the normal line or closer.
Oh, sorry. Further. Thank you. Okay, denser to less dense, further. Denser. This is denser to less dense, further away from the normal line. Thank you. Any other thing? Nothing, okay. No response, I consider okay. Now, we're gonna learn about the constant. Wait, Chung Wei. What's the difference between optical density and light density? Chung Wei, optical density memang light density. The difference is optical density and normal density. Normal physical density. Okay, so in terms of previously just now when we talk about the law of refraction, mana my pointer there. All right, the law of
Cher,
refraction. Mm-hmm.
Hua Yong asked a question in chat.
Why faster speed of light away from normal? Because it's moving. How to say why faster speed of light causes it to move away from the normal line? The analogy last time I used this is actually when, okay, since you actually mentioned this, let me refer back properly first before I say something that it's not proper. Okay, in terms of analogy that I used last time was actually the optical density. I consider is as parental control. Higher density means higher parental control when you go shopping center. When your parents parental control or your cash flow. Okay, so when you go shopping center, if your parents don't give you any cash, there's no money in your e-wallet, the Touch and Go also got no more money, you don't have the ATM card or whatsoever, which means your parents has higher power. So when that happens, you would follow closely towards your parents. But if your parents were to give you money inside your e-wallet, or probably they debited some money into your debit card or ATM card, then they said, okay, you go and buy whatever you want, then we'll meet back here at 1 hour. Will you stay next to your parents? Definitely no, right? So less optical density to me is more financial freedom, in the sense that your parents give you the money inside the debit card, and then you can go and buy whatever you want. So you will move away from your parents temporarily for that 2 periods. That's 2 hours, sorry. So that is actually how I memorized last time when I was in SPM, how I memorized that it refracts closer towards the normal or further away from the normal. The actual understanding, Hua Yong, I will let you know later on. Okay, because I was rushing time, I didn't really go and find out the detailed part on why faster speed of light it will move away from the normal line. Okay. All right. So I'm gonna proceed first, Hua Yong. Okay, so in this situation over here, when we talk about refractive of wave, finding for my pointer again. There it is. All right. So for refractive index determines the degree to which the light bends when traveling from vacuum to a medium. Please do take note, it's traveling from a vacuum, all right, to a medium. Vacuum means there is no air particles inside. When there's no air particles inside, the light wave will definitely move at the highest speed of light, all right? Speed of light in vacuum is 3 times 10 to the power of 8 meter per second, which means in 1 second, the time for you to close your eyes and open your eyes in 1 second, the light has already traveled 3 times 10 to the power of 8. That would be 0.3 kilo mega giga, 3 gigameters, right? Very, very far distance. Okay, so the refractive index is a degree to which the light bends when they travel from vacuum to another medium. So as such, we can actually define the refractive index as the ratio of the speed of light in vacuum to the speed of light in a medium. So refractive index n equals the speed of light in vacuum, all right? And another words over here, one key that I'm telling you right now, and you all please do take note. Vacuum is actually a less dense medium. Definitely less dense, is the least dense optical density medium. And other mediums is actually considered as a denser medium. Right? This formula for N, refractive index, by the end of today, you will know that there's 3 formulas for refractive index N. So the first formula is talking about speed of light in vacuum, which is 3 times 10 to the power of 8 meter per second, over the speed of light in the medium. So this is actually a denser medium, whereby vacuum is considered as a less dense medium. So please do take note of this. So when you're moving from a less dense medium to a denser medium, the speed in denser medium is actually much more slower compared to the speed of vacuum. So you're taking a bigger value, all right, which is actually 3 times 10 to the power of 8 meter per second, over a smaller value, which is whatever that is less than 3 times 10 to the power of 8. So when you take a bigger value divided by a smaller value, you will never get the value less than 1. The refractive index will never be less than 1. It can only be, the refractive angle N can only be greater or equals to 1. All right, optical density must be greater or equals to 1. All right, because the value of the refractive index will increase as n is always more than or equals to 1. I already mentioned this to you. The value of n depends on the wavelength lambda of the light used. Change in temperature can also cause the optical density and the refractive index of the medium to change. Okay, so vacuum and air has a refractive index of 1.00. So that's why I said that the refractive index will always be greater or equals to 1. Hey, to be more exact, actually, air's refractive index is 1.0003. All right. So because we always do calculation with two decimal places, so assume that the refractive index of air is equivalent to the refractive index of vacuum, which is 1.00. Then after that, we have olive oil. Before olive oil, actually, we have water. Water is actually 1.33. Olive oil is 1.46. Perspect or glass, all right, that's actually 1.5. Glass from crown, I'm not very quite sure about this crown and flint, right? The refractive index is much more higher, and the highest refractive index will always be diamond. And later on, you will know that diamond is actually the most sparkling and most twinkling material when light enters, is because its refractive index is very high. Okay, later this one we will talk about it in total internal reflection. Okay, so the next part of this, light rays traveling.
Sure.
Yes.
I have a reference book, right? And it says
Mhm.
the highest refractive index is gallium phosphide.
Mm-hmm. The highest refractive index is definitely something else. I'm talking about in terms of diamond. Why I mentioned diamond is because inside this particular table, this one is only the biggest right now. Not in
Oh,
the world. I'm not
okay,
talking
okay.
about the biggest refractive index in the world.
Okay.
And I'm sure there's other values also.
All right, thanks, Joe.
Okay, because normally when we do refractive index for SPM level, the highest value that we're going to use in SPM level is actually diamond. All right, we don't go bigger than that. Okay, seldom, not don't. All right, so light ray traveling from water into three different mediums. Okay, so here you can see water is actually traveling from mana pointer. Okay, traveling 1.33 towards perspect 1.5, which is from water to glass prism. Okay, you can see the angle actually changes. It's actually slight change only because the difference between the refractive index is actually quite small. Okay, from water to glass, which is flint glass, it actually gets closer towards a normal line. And then when it's actually from water to diamond, the refractive angle actually gets even smaller. So what I can say is that as the refractive index actually increases, the refracted ray actually decreases. Okay, as the refractive index increases, how I see increases, this value 1.5, 1.6, and also 2.52. 2.42. The refractive index increases, the refracted angle gets smaller and smaller. Okay, so from this, they actually did a ratio. They took a equation, all right, n1 means the medium, the first refractive index from medium 1, multiply by sine of the incidence angle. They found that the value is the same as the refractive index from the second medium. Sorry, wait for that. All right. The product of the refractive index and the sine of the refracted angle for the three different mediums are actually the same. All right, so please do take note about this. So from the laws of refraction of light, when the light travels from one medium to another medium, there is another formula for Snell's law. So for your information, actually, this is the basic, the first general formula for Snell's law, not the one that was previously introduced to you guys in lower science. Okay, so the actual Snell's law is actually n1 sine theta 1 equals to n2 sine theta 2, where n1 is the refractive index of medium 1, n2 refractive index of medium 2, theta 1 is the angle of the incidence in medium 1, and theta 2 is actually the angle of refraction in medium 1. So I'm going to open a whiteboard and I'm going to start scribbling something. Okay, Snell's law right now says that n1 sine theta 1 equals to n2 sine theta 2. So let's just say that this is my normal. All right, that's my boundary. This is air. Air means n equals to 1.00 to something else which we do not know. Okay, so when the incident angle comes, this is my theta 1, which I call it as my incident angle. Okay, give me a minute. All right, and then let's just say this one move away. So that's my refracted angle. I don't bother whether it's less dense or denser right now for the time being. All right, because it's moving from air to another material. So when it moves further away, right now, let's see. Should move closer. Because I'm moving from air to another material. So from less dense to denser, it's supposed to move closer towards the normal line. So the normal line between the normal line and the refracted angle, this is actually theta 2 from the latest formula. So this theta 2, I call it my refracted angle. Okay, so here n1 sine theta 1 equals to n2 sine theta 2. My n1 is actually 1.0. My sine theta 1 becomes sine I equals to my n2, I just label it as n. My sine theta 2 becomes my r, refracted angle. So when I rearrange this, 1 times sine I becomes sine I. The sine of the incident angle equals to n sine of the refracted angle. So when I rearrange the formula, I get n equals to sine I over sine r. The formula of Snell's law that you guys learned since lower secondary school. All right, lower science. Now, this one, that's why I said there's one assumption. When you use this formula, n equals to sine I over sine r, this assumption is that the incident angle I is actually at the less dense medium. Okay, less dense optical density medium. I have to train myself to say the correct phrase. Less dense optical density. And then R is actually located at a denser optical density medium. All right. So this is one thing that you guys have to be aware of. This is how the simplified version of Snell's law formula comes from. The basic one is actually n1 sine theta 1 over n2 sine theta 2. Okay. So now, if you guys need this in 3, 2, 1. Okay. So law of refraction over here, this is actually what I just wrote now. Okay. So this one I can skip already. Now, I already told you guys that Snell's law got 3 formulas. So we already had 2 formula. One which is n equals to c. Right. The first formula is actually n equals to speed of light in vacuum over speed of light in the medium. That's the first formula. The second formula is actually Snell's law simplified version or the longer version. N1 sine theta 1 equals to N2 sine theta 2. All right. Or the simplified version would be N equals to sine I over sine C. But be very careful about this. Okay. There's a reason why they introduced this formula out from the current syllabus, because previous syllabus, they did not introduce this n1 sine theta 1 equals to n2 sine theta 2. So again, because this is something that is being introduced out, so please do take note as you are just the second and the third batch of KSSM syllabus. All right, so now we're going to go into the third formula. Third formula is due to the depth of water. Now, we're not talking about water waves over here. We are still talking about light wave. So, real depth, what does real depth means? I take a beaker, I fill the beaker with water. All right, and then I put a coin at the bottom of the beaker. So, the real depth of the coin is actually from the surface, you measure it to the current position, the actual position of the coin. This is known as real depth. The coin is actually the object. All right, the coin is actually the object. But one problem is that normally when we look from above, the coin looks like as though it is somewhere higher. All right. So when the coin looks like it's somewhere higher, this is not the real object. This is actually just the image. Okay. So from the surface measure to the position of the image, that is known as apparent depth. All right. The main reason is because we look from above. All right. We actually look from above. So over here, that if any of you actually had the opportunity to go to the seaside, or previously when you look at the seaside, or if you look from the top view of the aquarium or the pond, you can see that the object, the fish, for example, the fish or the coral looks much more higher. All right, it looks like it's closer towards the surface. This is because of the refraction of light. So when the light rays from the fish is actually the object. All right, so light ray actually move from light ray will move from object towards the eye. Okay, so you have to understand this. Light ray move from the object towards the eye. So when this happens, all right, light ray from the fish will travel from the water to air. All right, because the object is actually at water. Water is actually a denser optical density, and air is actually a less dense optical density region. So moving from denser to less dense, normal line over here, it will move away from the normal line. All right, it will move away from the normal line. So light is refracted away from the normal line. The effect of refraction of light causes the image of the fish to be closer to the water surface as seen by the observer. All right, so when we see in a straight line. All right, so we see that as though that the fish is actually located somewhere higher because of the way that the light bends. But when we see in a straight line on ma, so we thought the fish is actually at a higher position. Okay, but the actual position is much more deeper. Okay, clear regarding this? All right. So in this picture, all right, what you have to understand why they put these two pictures inside the textbook is because they want to see who is looking at who. All right. If you're talking about the instructor, if the instructor is the observer, all right, if the instructor is the observer, then the diver is the object. So light ray will move from the diver towards the observer. So meaning means it's moving from a denser region to a less dense region. Moving from denser region to a less dense region, it will move away from the normal line. It will refract away from the normal line. So from the view of the observer, the diver's image is at higher position. And notice one here, we use dotted line. All right, we cannot use a solid line. Solid line is the actual path of light ray. Dotted line is what we imagine where it's supposed to be. Okay, so please take note, it cannot be a solid line. Now, if let's just say the observer is the diver is the one observing right now, looking above. Okay, so this is actually when you you are actually in the swimming pool and you're looking up towards someone that's standing at the side of the swimming pool. You can actually see as well that the person is actually much more higher. Why this thing happens? Because the instructor right now is the object. All right, so the light ray is moving from the object towards the observer. The light is actually moving from less dense to a denser region. When it's moving from less dense to a denser region, it will move closer towards the normal line. It will refract towards the normal line. So when it refracts towards the normal line, from the eye of the observer, they think that they are actually looking in a straight line. They think that they are looking in a straight line. So when it looks in a straight line, it looks like the instructor is actually at a higher position. Okay, so this is the difference between light traveling between in water situations. So you have to observe where the arrow is actually coming from and going towards. Okay, so obviously one thing, this whole entire chapter is talking about formulas also, especially refraction of light. So the third formula is actually here, the relationship between the refractive index of the medium with the real depth and apparent depth is here. Real depth is actually the bigger value, right? Real depth is much more deeper. Okay, real depth is actually much more deeper compared to the apparent depth, because it's the image of the object will normally be somewhere higher, so the apparent depth is actually much more shallow. So when you actually take a bigger value, deeper value over a shallow one, so obviously the refractive index will again be more or equals to 1. Okay, so definitely be more than 1 now. Okay, because if it's 1, it means that it's moving from air to air. Okay, so the third formula is real depth, the deeper value or the bigger value, over apparent depth, the smaller value. Now, please do take note one thing. All right, this is the part that I have to inform you guys. When, let's just say, they ask you to compare, all right, a same beaker, coin is located here, and then the only difference is actually the water level. Okay, now I'm gonna ask you guys to test one thing, and I want you guys to actually explain that. Mana? Okay, this is actually beaker number 1. This is beaker number 2. Okay, I'm gonna ask you a comparison question, and I want you guys to actually write that inside the chat box. All right, compare the real depth of the two beaker. Please kindly write this answer in the chat box. Compare the real depth of the two beaker.
Jill, you're muted.
I talk so much already. Thanks, Rebecca. All right. Now, so over here, the beaker are actually the same beaker, but the water volume inside the beakers are different. Volume in beaker 1 is actually more than beaker 2. So in order to measure real depth, we need to measure from the surface of the water down towards the position of the object. That is actually how we measure real depth. So over here, the real depth of beaker 1 is actually more compared to the real depth of beaker 2. Okay, so my answer, I would actually say the real depth in beaker 1 is more than beaker 2. Why? Because the verb, all right, or the comparison word that you're going to use for that. Okay, so obviously one thing, let's start. All right. Rabika says real depth in beaker 1 is more. She uses this symbol, all right, for real compared to the real depth in beaker 2. All right, this symbol can be used if it is in section A. Section A only can use this method that
Uh,
Rabika actually wrote.
Ch-
It's not allowed.
I was using that because I was lazy. Just so you know, I wouldn't do that in exam.
But then one thing, just to inform all of you, actually that symbol is allowed. That symbol is allowed only for section A. All right, but I would suggest you lah, don't use that symbol because it's confusing in section B. Okay, so try not to use this symbol, although it is allowed in section A. Section A only, section B tak boleh ya. All right, Chirong says the real depth is the same. Definitely salah already lor, Chirong. Okay, Adila says real depth of beaker 1 is larger than beaker 2. We are using depth. We are trying to measure depth. How come use the word larger? All right, that's the problem here when we are talking about depth. Okay, so if it's me, I could accept it, right? Because I'm not an English teacher, but I don't really like how that sentence means to me because the word larger means bigger. Okay, so Xiang actually used the word greater, which is much more acceptable. Real depth of beaker 1 is greater than real depth of beaker 2. You don't have to repeat real depth so many times. You can just say real depth of beaker 1 is greater than beaker 2. Sufficient. Ray's answer definitely wrong already because Chirong also gave the same answer. Chongwei says real depth in beaker 1 and beaker 2 is equal. Also salah. Brian says real depth of beaker 1 will be greater than real depth of beaker 2. Brian, why the word will be? Sorry regarding the background noise. Right? Why do you use the word will be? So does it mean that it is not greater right now? Okay? Please don't play English lah, alright? Okay, now, so in this case, I hope you guys understand what I'm trying to teach you guys how to write. Especially for depth, it's very, very sensitive. The word that you're going to use to describe the depth, okay? Don't use higher depth, lower depth. Okay, now let's get back to here. Where's my mouse again? Okay, now, so refractive index has three formulas right now. We have sine I, this is the normal one, the simple one. Sine I over sine R equals to refractive index, or the complete one is N1 sine theta 1 equals to N2 sine theta 2. Okay, that's for if it's actually there's an angle over there. But if they give you speed, okay, if they actually give you speed, sorry, let me silent properly. If they give you speed when it's moving two different mediums, then you actually use velocity of light in vacuum over velocity of light in medium. Remember, the faster speed over the lesser, the slower speed. All right. So refractive index has no unit. Refractive index is one of the few physical quantity that does not have unit. All right. It's an indication of the light bending ability of the medium as the ray of light enters its surface from air. All right. So refractive index has no medium. Okay. The third one is actually real depth and apparent depth. Okay. Anyway, one thing, refractive index is not a physical quantity. Yeah. Because it cannot be measured. It's received from others, is derived out from other physical quantity. I suddenly saw Chirong's message. Is deeper accepted. Real depth of beaker 1 is deeper than beaker 2. Can, that one accepted. But try to use the word more, greater is much more better. Okay, if that teacher's English is not strong, all right, much more weaker, don't understand the English word so much, then the teacher might give you a wrong law in the exam. Okay, if in school internal exam you're gonna cause me to have a headache, or if it's SPM, then I think there's either yes or no only lah. All right, so for real depth and apparent depth, okay, real depth is much more at a deeper position. All right, apparent depth is much more higher. All right, which means the apparent depth is actually less compared to the real depth. So the formula is actually capital H. Capital H stands for real. And small h stands for apparent. Apparent means the position of the object, image, sorry. All right, apparent is actually the depth of the image, while real depth is the depth of the real object. Okay, so this is actually the formula for refractive index. Okay, I'm gonna try to ask you guys to do this question right now. Very, very quickly, just write the answer down in the chat box, whoever that can. All right. Diagram 1 shows a spoon appears bent in water due to light phenomena. Okay, now thank you for those who usually respond to me. Chongwei, ROL also can consider as reflection of light. Okay, so over here, all right, the word bend actually is a keyword that is refraction. All right, so the correct answer of the phenomena is actually refraction of light. Okay, those who actually answered refraction alone, is very dangerous to write the answer refraction alone, all right? So please do write in the proper one, refraction of light, if this is an open-ended question. Okay, now state one physical quantity that changes when light propagates from water to air. What physical quantity will change from when it moves from water to air? There's a few answers. Speed of light, good, correct. Some more? What else? Velocity and speed both is acceptable. There's something else that changes. What else? Direction. Can we measure direction? Direction can't be measured. Because the direction is, how to say, direction is actually one of the characteristic. Good. All right, Adelia, angle of the ray changes. Darren also correct, wavelength changes. Chongwei closer to normal line and further, that one is actually the angle. We don't use direction, but we use the word angle. The refracted angle changes. All right, wavelength also correct. Velocity also correct. Density, density doesn't change from, in my opinion. All right, they are talking about the physical quantity that changes when light. They are talking about the light's physical quantity when it moves from water to air. So I will not accept density answer. Okay, so the one that changes, again, mana my pointer. All right, the one that changes is wavelength. Dash luminosity is a bit, we don't cover that in SPM. All right, we don't cover luminosity in SPM. All right, even though the intensity of light is actually luminosity, but we don't cover that physical quantity in SPM level. All right, so answer is actually wavelength. You can actually use wave speed. I will also accept the answer of speed. I will also accept the answer of velocity. And I will answer the angle of light ray. All right, so this is quite an open-ended, even though it's just said once one answer. Now, the next part is actually complete the ray diagram to show the refraction of light that occurs on the spoon. So they did give you the object and the image already, okay? So I'm going to come out from PowerPoint because I want to use the ruler outside. So I'm going to keluar sekejap. Okay, so I'm going to show you how I answer this. Now, first, I'm going to take the ruler out. Okay, so first thing first, I'm going to put this at the normal line. Okay, so I'm going to draw the image. You would notice that the image is already there. So I'm going to use purple color so that it's easier for you guys to see. So I'm going to draw the dotted line from the image to that point where it touches the boundary and the normal line. That one has to be dotted line. The one that going towards the image for refraction of wave have to be dotted line. And then after that, the same position over here at this point, I let the angle go towards the object. So I draw this line towards the object. And because it's actually moving from object to, okay. Because it's moving from the object towards the eye, so I need to have the arrow. All right, the question is a 2-mark question. See, 2-mark question. So the marks is actually given for the dotted line of the image. This one should be a straight line. So which means I'm going to use a ruler if this kind of question comes out. All right, I'm going to use a ruler to make sure that this is a dotted line. So this is the 1 mark here. And then from the object to this intersection point with the arrow drawn, then you can get a 2nd mark. Okay, for your information, this question is actually last year trial 2021 question. I've forgotten which state lah, okay? All right, so this is actually for refraction of wave. So give me rest my throat for about 4 minutes. All right, then we will come back and cover total internal reflection. All right, so see you guys in 9:15. Okay, let's get back to total internal reflection, the second subtopic of light chapter. All right, so for total internal reflection, I hope you guys are already back. Okay, now I'm using this simulation to show you guys what is total internal reflection. So now total internal reflection right now is at the top position or at the top medium where my laser pointer is located. My laser pointer is indicating it as an object. So I'm gonna let that to be glass, higher density. All right, and then I let this be air, okay, or somewhere between that. All right, so it's actually now the light ray is moving from denser to less dense region. So when it's actually moving from denser to less dense region, now this is at the normal line. It's incident at the normal line. So when I actually move it to an angle, so this is my normal line. Okay, so when there's an incident angle created, okay, so I'm gonna bring this out and I'm gonna start scribbling stuff. Okay, so from the normal line to the side, that is actually the incident angle. This one is actually the refracted angle. And you will notice one thing as well. There's a very thin, lighter line over there. This is actually a partial, or yeah, this is actually a partially refracted angle. All right, incident angle. This is actually a partial refracted ray. Why do I keep using angle? I'm a bit confused today. This is refracted ray. So from the normal line to the refracted ray, that would be the refracted angle R. So this one is actually I. Okay, so you would notice one thing. As my laser move further away, which means as my incidence angle increases, my refracted angle also increases. So as I move it, as the incident angle increases, my refracted angle will move even further away from the normal line. So when I reach a certain position, you will notice that as I move away further and further and further, one, my refracted angle increases a lot. And then do you notice that the reflected ray actually gets more obvious? Okay, because the intensity actually increases already. This intensity actually decreases. The percentage is already at 49%. Comparing to when it's further away, the intensity is only 3%. It's much more brighter already. So as I increase my incident angle, my refracted angle will also move away from the normal line until one certain position. I'm gonna get that. Okay. Very difficult to get the angle. All right, until one certain position whereby the refracted angle is actually 90 degrees. Okay, this one cannot show the 90 degrees. Let me reopen. I borrow close. I thought I don't need to use that. Let's see if I can do this here. This one cannot. Okay, top I put it as oil. Bottom I put it as water. Okay, probably diamond. Easier. Okay. So as I move it, this one also doesn't show. This is the best that I can show you lah. Sorry, yeah. Okay, so when the refracted angle is 90 degrees, this angle actually there's a answer there's another name for the incident angle. But what I want you to focus on right now is that, do you notice that this is actually moving from a denser region to a less dense region? It's supposed to undergo refraction. All right, it's supposed to refract. All right, the light's supposed to bend when it enters another medium. But then when I actually reach a certain position, the light is actually fully reflected back into the denser medium itself. All right. So from it's supposed to refract out. All right. It's supposed to move out to the other medium, but then right now it totally reflected back in. Okay. So this scenario, this phenomena is what we called it as a total internal reflection. Okay. We call this as total internal reflection. So the image that is being shown by the textbook, right, where the reflected image of the turtle can be seen on the boundary of the water and air. So we are actually the cameraman is actually beside the turtle. So the cameraman is actually inside the water region as well. The camera is also inside the water region. So it's actually looking from the water up towards the air. And then they can see the reflection of the turtle exactly at the surface boundary over there. So this is actually known as total internal reflection. All right, total internal reflection of light only occurs when light travels from a high optical density to a low optical density. The key word, the condition for total internal reflection to happen is that it's moving from a high optical density to a low optical density region. All right, so that is the first condition for total internal reflection. Next, all right, so from this is the first thing that happened just now that I showed you guys. When the incidence angle is less than the critical angle we'll discuss in a short while, the ray is refracted away from the normal line. Normal refraction will occur. All right, when the incidence angle is less than the critical angle, this is a normal refraction of light. All right, this is a normal refraction of light. So the rays will refract away from the normal line because it's moving from a denser region, all right, a denser optical density to a less dense optical density. So it will refract away from the normal line. So a weak reflected ray can be detected, all right, because this is a boundary. All right, when it's a boundary, reflection will occur also. All right, real life situation reflection will occur also. All right, so another way to say this is that when light travels from denser medium to a less dense medium, it bends away from the normal. Textbook used the word refracted away. So last time we used to use the word bend away. Both is still acceptable. A small part of the incident ray is reflected inside the glass, and the angle of refraction is greater than the incidence angle. Critical angle is not the refracted angle. That's another meaning of it. Okay, but if there's one situation, as the incident angle increases, the refracted angle will also continue to increase until a certain position whereby the refracted angle is actually 90 degrees from the normal line. From the normal line, it is 90 degrees, which means the refracted angle is at the boundary. All right, it's at the surface, the boundary between the air and the glass. When this happens, the incidence angle is known as the critical angle. I repeat, when the incidence angle increases, the refracted ray will continue to increase. All right, because moving from denser optical density to less optical density, it will refract away from the normal line. So as the incident increases, refracted angle increases until when the refracted angle is 90 degrees, the incident angle is known as the critical angle. And this situation, it is still refraction, This category is still refraction of light. Why? Because you still have the refracted ray, which is actually 90 degrees. Okay, so that is actually what is explained at the bottom part. As I keeps on increasing, our refracted angle increases, the refracted ray moves further away from the normal line, thus approaches the glass air boundary. So the refracted ray travels along the glass air boundary. This is the limit of the light ray that can be refracted. As the air All right, as the angle in the air cannot be any larger than 90 degrees already. So this situation of incidence angle is actually known as the critical angle. Okay. And then when it's critical angle, if the incident angle continue to increase, if the incident angle continues to increase on more than the critical angle value, all right, then it's going to be total internal reflection. The ray will be totally reflected back. There is no longer refraction happening here. All right, there's no refraction of light anymore. This is when incident angle greater than the critical angle. So total internal reflection happens here. So please do take note. This situation is still refraction of light. The refracted angle is still 90 degrees. Okay? Only when the incident angle is bigger than the critical angle, then only it will happen total internal reflection. Take note. Okay? So if the angle of the incident increase further, greater than the critical angle, the light is not refracted anymore, but is internally reflected back. So this phenomena is called the total internal reflection. Okay, so here, total internal reflection, a few things that I want to clarify. Total internal reflection at the surface of a medium when the angle of the incident in a medium exceeds, mana my pointer pergi again. All right, condition here, total internal reflection of light at the surface in a medium when the angle of incident in the denser medium exceeds a critical angle. Okay, so two conditions for total internal reflection to occur. Number one, light ray enter from a denser optical density medium towards a less optical density medium. Number two, angle of incidence is greater than the critical angle of the medium. Okay, so these are the two conditions of total internal reflection. Please memorize this. Okay, the phenomena of total internal reflection happens, whatever that's mentioned above, but I want to focus here is the critical angle. Now, critical angle definition is the angle of incidence in the medium of high optical density when the angle of refraction in a medium of lower optical density is equal to 90 degrees. So please memorize critical angle definition and total internal reflection definition and the two conditions. All right, so it's very important for you to understand this. Total internal reflection is a very famous question. It repeatedly keeps coming out. Okay, so please do take note on this. Now, formula in total internal reflection, because it is refraction and then after that it undergoes reflection. Total internal reflection, the formula normally used to calculate the critical angle. So I'm going to open up a PowerPoint here. All right, and I'm going to use back Snell's Law general formula. N1 equals to sine theta 1 equals to N2 sine theta 2. All right, so the boundary that we have is the unknown material, the denser material moving to air, which is actually 1.00. Okay, so this is the normal line, the incidence angle, and then the refracted angle is actually at the boundary. So this is 90 degrees. So N1 is here. So N1, this is the critical angle. When the refracted angle is 90 degrees, the incidence angle is known as the critical angle. Okay, so N1 sine theta 1, which is here, the top region, equals to N2 sine theta 2. So N1 is value of 1.00. Sine theta 1 is sine 90 degrees. N2 is our unknown medium. Sine theta 2, the incidence angle, theta 2 is actually the critical angle, so that's sine C. So 1 of sine 90 degrees, sine 90 degrees is actually 1. So 1 times 1 is still 1. So this is 1 over n sine C. So I want to know the refractive index. It will be n equals to 1 over sine C. If you don't, 1 over n sine C, 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 1 over n if you are finding for the refractive index. If you're not finding for the refractive index, but you're finding for sine C, then the formula would be sine C equals to 1 over n, and then C is equals to inverse of 1 over n. So you have to use your calculator for this lah. All right, so this is actually how they get the formula out. So remember, this critical angle is to find when the refracted angle is 90 degrees. Okay, only when the incident angle greater than the critical angle, then only total internal reflection can happen. All right, so I hope you guys clarify on this. So let's go back to here. Do you all need to copy this? Screenshot in 5, 4, 3, 2, 1. All right, so in general, the relationship between the critical angle and the refractive index is this formula. So I have just derived out how did they get that formula out for you. So like for example, diamond. Diamond refractive index is 2.42. So 1 over 2.42, you get 0.4132. So sine inverse of 0.4132, the angle is 24.4 degrees. So this means that if let's just say I have a diamond, okay, I have a diamond and light ray actually enters the diamond. Light rays enter the diamond, and then when the incident angle I is greater than 24.4, then it will be reflected. The refracted angle will be the same as the incident angle. Then it will keep on bouncing inside until it managed to get out. That's why normally diamond sparkles. All right, diamond sparkles is because their critical angle is very small. When a single light ray enters the diamond, it will enter inside and it will keep on reflecting inside there, bouncing a lot. So that's the reason why diamond actually sparkles. The more that they cut the surface of the diamond, the more difficult light can come out back from the diamond itself. So which means the more cutting they have, total internal reflection will occur even more inside the diamond, and that's how the diamond sparkles even more. All right, so here, okay, the higher the refractive index of a medium, the smaller the critical angle of the medium. Okay, so because here n equals to 1 over sine c. So this is inversely proportionate. The higher the refractive index, the smaller the critical angle. Okay, so all right, I have to stop here already. It's already 9:30. So 2 days later, today's Friday. So on Sunday, we'll continue on with the application of total internal reflection and the next subtopic. Okay, so up to here, is there any question that you guys want to ask me?